So IO Volcano Observer, follow the heat. The key players are the University of Arizona, APL, UCLA, JPL, DLR, University of Bern, and USGS. Next slide. So our overriding science objective is to understand how tidal heating shapes worlds as a fundamental planetary process. And the number one issue is to understand IO's internal structure. I'll say more about different models for IO's interior. List here are our 5 main science objectives. So determine the degree and distribution of melt within IO's interior, determine IO's lithospheric structure, how and where IO is losing heat. Then we want to measure IO's orbit evolution and volatile loss. Next slide. So everyone probably already knows that IO is special. That's because of the Laplace resonance with Europa and Ganymede, resulting in intense tidal heating. And IO is the best place to understand tidal heating because it's most extreme there, and we can easily measure the tides, the heat flow, the mass loss, etc. Also, large-scale silicate volcanism has been a key process on all of the terrestrial planets, but IO is the only place in this solar system, at least, where we can watch such activity. And the heat pipe tectonic end member is relevant to the early terrestrial planets and present-day exoplanets. Next slide. So there are hundreds, I think 250 extremely active volcanic centers on Io, by which I mean more active than Kilauea, which over the long term has been the most active volcano on Earth. Kilauea is less than 1 gigawatt power, whereas these go up to 10,000 gigawatts and more. Next slide. There are also very large lava flows on Io that are active today. So Amarani Maui is the largest active lava flow known in the solar system, unless there's an even bigger active one, probably on Io. That's compared on the left to the Pu'uo'o flow field in Hawaii, the longest currently active flow on Earth, and the 1783 Laki flow field, the longest flow observed by people. But in the past, there have been such comparably large lava flows on Earth, which have done important things to Earth, like mass extinctions. And there are also large lava flows, ancient lava flows on the Moon, Mars, Mercury, and Venus, shown here as an example on the Moon. Next slide. Okay, so Io's interior structure. This is really the first order question for understanding tidal heating. On the right are shown 4 different models. On the left are 2 models that are basically a solid mantle for Io. On the right, we have much more magma-rich models. We can have a true magma ocean in which the lithosphere is detached, or if there could conceivably some sort of magma sponge where you have voluminous interconnected magma, but it's within a solid matrix. Or if the mantle is solid, it could be deep mantle heating resulting in greater polar volcanism and heat flow, or it could be asthenospheric, shallower mantle resulting in more equatorial heat flow and volcanism. So we have these 4 models, and we have a series of measurements from IVO of tidal deformation, libration amplitude, magnetic induction, dominant lava type, and heat flow distribution. And together those uniquely distinguish between these 4 models. Next slide. So the heat pipe end member is thought to be a 3rd major end member for how planets lose heat and controlling the tectonic style of the planet. So there's plate tectonics like Earth, there's conduction, stagnant lid, which characterizes the Moon, Mars, and Mercury today. And then there's heat pipe volcanism from Io today, and what's thought to have applied to the Hadean Earth and the early Moon and other planets, which have then migrated towards stagnant lid. Then Europa and Venus are somewhere in the middle of this. We don't know very well. The basic mechanism here is very simple. You just have so much volcanism that erupts and spreads out. It cools, And you have vertically subsiding lava flows that's faster than the conducted heat flow. And the result is that you can have what seemed contradictory initially was when we saw the big mountains on Io, you can have a very cool and thick lithosphere in spite of this high heat flow with this mechanism. Next slide. So we can determine the thickness and rigidity of Io's lithosphere from a combination of techniques, including tidal K2 and libration amplitude and the magnetic induction signature. And so the intersection of these three measurements provides a very tight constraint on both lithospheric thickness and rigidity. So this is a key test of the heat pipe model. If Io's lithosphere is not high rigidity, then we have a real puzzle to understand. Next slide. So the science experiments for the baseline mission consist of a narrow angle camera with 12 colors, a thermal mapper with 10 band passes, including a radiometer as well as the bolometer. Both the NAC and the T-map are mounted on a plus or minus degrees pivot, which along with twisting the spacecraft about the z-axis to keep the solar rays at the sun allows us to point anywhere we want to. In addition to that, we have the dual flux gate magnetometer, a plasma instrument for magnetic sounding, which together do the magnetic sounding, an ion and neutral mass spectrometer contributed from the University of Bern. The T-map is contributed from DLR in Germany. And then gravity science is a 6th major experiment using spacecraft hardware. We are proposing now in phase A 2 optional instruments. One is a student collaboration wide angle camera, SWAC, and a reflective UV spatial heterodyne spectrometer rushes as a technology demonstration option. Next slide. So the IVO's orbit is optimized for both science and to minimize the total radiation dose. So it's an orbit that's inclined 45 degrees to Jupiter's orbital plane. This results in north-south flybys, basically past Io, which has significant advantages. It minimizes the total radiation dose per flyby. It's about 20 Krad per flyby versus about 80 for Galileo or 70 for Europa Clipper. The spacecraft only spends about 12 hours per day in the intense radiation. So, and that's also advantageous for observations that are sensitive to radiation-induced noise. And then we get great observations of the polar regions, which are poorly observed and are key for distinguishing tidal heating mechanisms. Next slide. So we really optimized this orbit to achieve our science. In particular, to measure tidal K2, we want to pass over the right places at the right times. So the right places are shown at the map on the right, which shows the maximum difference from periaps to apoaps in the gravitational signal and MGAL. So we want to fly over those bright red areas. Then the right times are near periaps and apoaps. And we want to do that twice because if something goes wrong either on the spacecraft or the DSN, on either of a pair, it's a problem, so we want 2 pairs. So this drove us to about a greater than 3-year tour in order to really optimize this. These are optimizations. You need a dedicated mission to do this. Juno cannot optimize in these ways. A side benefit of this longer tour is that the subsolar longitude moves significantly, and we can actually image more than 90% of Io in either sunlight or Jupiter shine. Jupiter shine is with low phase angle. Jupiter is comparable to the illumination of Erekos by New Horizons recently. Next slide. So we have a tour with 10 flybys, all of these carefully chosen to achieve the science, not only gravity science, but for the libration, we want different true anomaly pairs to optimize that. We want them distributed over Io. We want a set of flybys on the trailing hemisphere for the magnetic induction experiment. We want high magnetic latitudes also for that magnetic induction. And we've come up with a tour here that we want some night side passes for lava temperatures. And so we spent a lot of time on this and put together the tour you see here. Yellow is dayside illumination. This is just plus or minus 10 minutes, by the way, the ground tracks here. Dark blue is night side. Light blue is Jupiter shine with low phase angle Jupiter. Next slide. So we get nearly global image coverage. Here's a map here of resolution over IO. So we cover some 90% of IO at better than about 300 meters per pixel, actually, with a section of that in the leading hemisphere being by Jupiter shine. With an extended mission, we can cover that in daytime. And then also shown in the upper right is the wide-angle camera stereo coverage, which is quite exciting. This is a long-track stereo with matching illumination. That's the stereo at better than 0.5 kilometer per pixel. Next slide. So in summary, IVO can provide a rich science return relevant to understanding terrestrial planets, ocean worlds, and exoplanets. This mission accomplishes all of the objectives in the decadal survey for a New Frontiers class IO mission. It actually improves over that concept, such as by measuring tidal gravity, libration amplitude, lava composition from thermal emission spectra, and with the global mapping. Now is a great time to start this mission because there's been a lot of technology advances for high radiation environments, for a series of other missions that are now either in flight or soon to launch. Also, by being in the system jointly with JUICE and Europa Clipper, this improves the science return from all three missions, in particular for measuring the orbit migration of Io, Europa, and Ganymede. This can tell us whether the Laplace resonance is in equilibrium or not. That's a fundamental question for all three satellites. And by launching in the late 2020s, we get a Mars gravity assist that saves a bunch of fuel. We can have an extended mission, a substantial extended mission with, we expect, 10 additional IO encounters.